Hi guys, today we're going to talk about shapes and stereoisomerism, okay? Stereochemistry, okay? And of course, let's start with shapes as we've done this before. As I said, the structure of the complex ion depends, of course, on the formula, the molecular formula of the complex ion. Now, in this case here, the molecular formula of this one here, silver diamine here, right, and copper 1 chloride here is linear because condition number is 2. It's like here, right? Silver 1 to 2. So 2 here, 2 negative bonds here. Why is this complex? Because the coordination number 2, okay, is larger than the normal covalency, okay, which is 1. So this is a complex ion. Same as here, copper 1 is copper 1. Copper 1 is very rare, okay, but it exists, okay, quite stable here, right? So 2 of them greater than 1, that means complex ion, right? So linear, and if there are 4 coordination number 4 or 4 ligands joining to it, right? Okay, they can be tetrahedral, and then there's 4 also can be square planar. 6 octahedral. Okay, now quite good to remember for tetrahedral is C. That is Cl is copper 2 plus, okay, cobalt 2 plus, and chromium 3 plus. All the chlorides are tetrahedral. Okay, square planar commonly is nickel and platinum. Now, this is how square planar looks like. Okay, square planar, the angle here is 90. Of course, if it's tetrahedral, like a copper tetrachloride, right? It will be, of course, 109.5. Okay, so of course, octahedral with a 6 condition number, right? Common one, of course, is you can see here. Okay, octahedral you have seen before, is it? Okay, so now let's look at some of this isomerism that's available for us. One is called structural isomerism, cis-trans isomerism, or geometric isomerism. Sometimes there's also one more called Mer and Fa, F-A-C, okay, whatever. Optical isomerism. Okay. Now, when do we see structural isomerism? What do we mean by structural isomerism? Definition: same molecular formula, different structural formula. Okay, it's a definition for structural isomerism. Now, the first 2 examples are here. Okay, it's cobalt 3, NH3, cobalt 3, right? NH3 bracket 4, 4 ammonia, 2 chlorine, and 1 bromine. Of course, chlorine is minus here, is minus here. This is charge 0. So the whole thing is plus 3, or 3 plus here. The whole thing will be charged 0, isn't it? The whole thing. Right? Now this is called the molecular formula. Now, to write, this is how you write the molecular formula. Cobalt, NH3, 4, Cl2, Br. Now, whenever you see this is obviously an octahedral complex. Whenever you see the number exceeds 6, 4 plus 2 plus 1 is 7, isn't it? Right? So for it to form an octahedral, 6 must be bonded to the cobalt and 1 should be outside. So what are some chances? Okay, now there are 3. There are 3 structural isomerism that you can play with 3. One, of course, if you keep all the 4 ammonia inside and then the 2 chlorine here, right? Which means the whole thing is 3 plus and minus 2 give you plus 1 here. So the bromine is outside. Bromine here is an ion, attracted to it by just ionic bonds. But the chlorine and the NH3 are attracted by strong coordinate covalent bonds or dative bonds. Of course, the other one would be when chlorine and bromine exchange each other. So you have chlorine minus 1, bromine minus 1, and what's Cl here? Okay. So in this case here, same thing is plus 3 plus, minus 1, the whole thing is plus 1, chlorine is minus 1. So this whole thing is charged 0. So now this one here and this one here are different because this one is 1 Cl and 1 Br. Okay. So in this case here, these 2 are structural isomerism. Same molecular formula. No? These two have the same molecular formula here. Okay, now how do you draw the structural isomerism for these two complex ion? Now, in this case here, you don't put the Br minus side, which is this one here. See now? So cobalt here, 4 ammonia here from the dative bond here. Okay, and Cl can be on top, is minus, okay, and bottom. Right? Now, because they are on top and the bottom, they call it the trans isomer. Okay, right? So this one here, of course, remember these two having the same molecular formula, which is this one here. Okay, this one here. Right? So now the other one, of course, is Cl on top here, and this one is 90 degrees here. Now this is called the cis isomer. Okay, 90 degrees. Here the angle is 120 or 180. Okay, so now these two are what? These two are structural isomers, right? Sorry, these two are cis-trans isomers, but this one and this one here is structural isomers. Now, how about this one here? Okay, this one here, I think I draw up here. Okay, remember? Now I got cobalt here, 4 ammonia here. Okay, now the first one, which is the cis-trans isomer, is chlorine on top here and bromine on bottom here. Okay, the second one, of course, is when the chlorine on top here and the bromine here, which is 90 degrees here. So this is the cis isomer, this is a trans isomer. Right? These two are cis-trans isomers, okay, for this formula here. But this one, I put green color, right? This one and this one here are what? Structural isomers. Okay, isomers. Of what? Of this formula. Okay. Now, of course, there's one more. If you look at it here, there's one more. If all of it go inside here, like here, right here, okay, where ammonia, one ammonia comes out, and of course, this whole thing is charged, right? So this whole thing here, but normally it wouldn't exist because why? Because it's all neutral. Okay, this one will move off. But now, mind, so we took about this. What I found in nature is this one here and this one here. Okay, these are structural isomerism. Now, this question here, this theory here, found one book, the old book called Chemistry in Context. It's a very good book. It gives you the structural isomers of this compound. Okay, I remember see this chromium trichloride 6 water molecules here. So the water molecules are holding is who is attached to the chromium 3+. This 3+ here. Okay, right? So they found out that there are 3 possible structural isomers. Remember now, this formula here is called the what? Called the molecular formula. Okay, it's called the molecular formula. So 1 mole of this chromium trichloride will have 1 mole of chromium, 3 moles of chlorine, and 6 moles of water. This is called the molecular formula. But they exist in 3 forms. 1, 2, 3, in 3 structures. The first one, of course, is, we take the first one here, okay, where this one here, all the water is daily bonded to chromium like here. Chromium, 3+, and 1 water, 2 water, 3, 4, 5, 6 octahedral complex. Okay, so the water is neutral, so the whole thing for this complex is 3 positive charge, and we have the 3 Cl minus attached to it by ionic bonds. Okay, 3 Cl minus here. So this whole thing here is still have a formula of what? Cr Cl3 full stop 6 H2O. This is the molecular formula. This one is the first structural formula of this molecular formula, which is the complex ion here. Now, the second one is that when one of the chlorine here goes inside and exchange 1 mole of water here. So 2 chlorine minus remain here and 1 water coming out here. And then 1 chlorine enters here. Okay, Cr H2O5 Cl. The whole thing is 2 minus. Why? This 3+. chlorine is 1 minus, so the total is what is 2 plus here. Okay, so for this one here, what is the formula? As well, it's very simple. Just replace one of the things here. Like here, just replace one of the things. I put blue better. Or flatten my throat. Okay, Cr here. Just put anywhere. Chlorine here. Okay, the rest is water. So there's no cis-trans isomer. There's just a normal octahedral complex. Okay. Okay. So octahedral means that there are 8 sides. One side here. Okay. One side here. The triangle there is a face. There's 4 faces at the top, 4 faces at the bottom, so 8. So it's not octahedral. Okay. So now this is for this one here, right? The 2. The third one, of course, if another chlorine exchanges from the water here. So here, 4 water only compared to 6 here. So 2 water comes out. So this one here will now be the structure of the complex ion, right? It's actually called Ma4B2. This is called Ma6. This is called Ma5B. Okay, I mean the general formula. M means the transition metal ion. A means A and B are the 2 ligands. Okay, so in this case here, right, the possibility of cis and trans, like here. Now remember this one here. I'll draw it out for you already. Chromium here, Cr3 plus. So there are 2 chlorines here, one on top here, one on bottom. This is octahedral because of 6, chlorine number 6 in it, so it has to be octahedral. So where can I put the chlorine on top and inside here? Okay, if I put Cl and Cl, look at same thing. It's octahedral. So top and side here, the angle is 90, right? The rest of them are all water. Okay, so because it's 90 degrees here, it's a cis isomer. Now you put the chlorine on top and on the bottom, right? The angle here is what, 180. Now this is called trans isomer. Here all the water here. So it's octahedral complex, right? These 2 are cis-trans isomer. Cis-trans. Okay? Isomer. So for this number 3, this structural isomer, there are 2 possible isomers also, which is cis-trans isomer. All together, there are of course 3 structural isomers. Okay. Now remember this question came out. I'll show you. Yeah? Now the color is all different. No, this is blue, gray, or violet. This is pale green. It's green. And of course, the Cl minus here, it comes out when you dissolve water. The Cl minus will come out as a free Cl minus ion, and it can be shown by just using silver nitrate in the question it says here, which will react to give you a silver chloride, which is a Pt3. 1 mole. Here, there are 2 moles of free Cl minus. Here are 3 moles, and they use this idea to actually find out which is the structural isomers afterwards. Okay, so 1 mole silver chloride precipitate is 2 moles, and these 3 moles here. Okay, of course, conductivity also is different. This is 2. Why? Because one of the red color. Okay, why conductivity is 2? Because 1 plus here is 1 ion, 1 Cl minus here, 2 ion. Yeah. That is 3 conductivity. Why? It's 1, 2 plus, and 2 Cl minus here. So it's 3. So it's 4 conductivity. Why? There's 3 Cl minus and 1 3 plus here. Okay. So you can see structural isomers can also exist as cis-trans isomers for octahedral complex. Now, let me show you how this fantastic, simple thing appear in your exams. Okay, let's look at page 139. Okay, 139 in your past question. Now, see, if you have a foreknowledge of that idea, to do this is very simple. But if you first time look at this, then you better think carefully, okay? Because unless you can think well, you maybe have some problems with it. Okay, now let's read together, okay? A number of isomers with the formula. So now this formula CrH2O6Cl3, this is the molecular formula, okay? This is the molecular formula, right? The whole thing. They didn't tell you who is bonded to who, okay? Exists. their general formula is this one here. Now, all these numbers here can be quite, quite scary. CrH2O 6 minus N and Cl N and then bracket Cl. When you put the bracket inside, that means that this will be a complex ion. Okay, right? The rest of them are outside the ion. Okay, so the N here, well, depending on what the number of N is, now they will explain to you. Each isomer contains 6 coordinated. That means 6 means octahedral already, okay? Octahedral complex. We'll explain to you this various of them. Water molecules are not directly attached to a Cr atom. Okay, the water molecules are held in the crystal lattice as water crystallization. Okay, so right, so here the Cr-Cl bond is not easily broken. So if they are attached, now this one of course is a dative bond. So if the dative bond they're very strong, they cannot be broken. So the chloride bonded to Cr3 plus in the complex do not react. They tell you already, which means the one here, outside it, which is a Cl minus, will react with a silver nitrate. Clear? Okay. Now, so this is what I tell you. All right. Now, let me just go over. So when you take this question here, you will think, okay, now this and this are about the same. Except this one, they say that, well, here there's no differentiation of the different kind of isomers. Right? Now here, if N is equal to 0, the first one here, right? N equals 0, that means water here is 6 here, right? 0, that means there's no chlorine attached to the chromium in this complex here. N equals 0, that means Cl, the 3 here, okay? Which means this is actually, you can put Cl 3 at the bottom, right? Right, 3 Cl. And water, since 0 here, there's no water crystallization. It means all the water inside here. So this is the first one, if N equals to 0. It means in this case here, right, in this case here, the complex ion is just, all right, this one here. So in your mind, you must know the theory, Cr, okay, water, and on top here is water as well. Okay, of course it's 3 plus. The whole thing here is 3 plus here. Okay, now this is your structure. It's an octahedral structure. Octahedral. This is all they want. Okay, complex, the octahedral complex ion. The first one, when N equals to 0. Okay, where the 3 chlorine ions here will react with your silver, 3 silver, to form 3 moles of silver chloride. Yeah. Now the second one, of course, is when N equals to 1. Okay, so you must think ahead, right? When N equals to 1, okay, N equals to 1, what happens? Right, water will be 6 minus 1, which is 5. Okay, I use blue, so you can see easier. So 5. Cl and N is 1, so Cl here. All right. The outside Cl, 3 minus 1 is 2. Obviously, this can put Cl2 like that. N is 1, so it's 1 water here. Okay. So in this case here, what would be the structure for this one here? So we just concern about the structure of this fellow here, which is like that. Okay. Got 5 water there. All right. Water. 5 of them, water, and here will be a Cl. This whole thing here, this is a complex ion shape. This plus 3, 3 plus here, 1 minus here, this will be plus 2, 2 plus here. Okay, so of course this one will give out 2 moles of Cl minus. The this one here will plus your silver, give you 2 moles of silver chloride. Yeah. Okay. It's also octahedral complex. These two are octahedral complex. Octahedral. Okay. Angle between them is 90, 90, 90. Okay. Right. So these two comes out. Now the next one, of course, is this one here, where N equals to 2. When N equals to 2, water is 6 minus 2 is 4. So 4 here. Okay, and NO2Cl is 2 here. All right, NO2 3 minus 2 is 1. It means 1 Cl minus outside. NO2 got 2 water here. So this formula here, you need to substitute the N inside here to actually write out all the formulas here. Okay, right? Right, now there is no, okay, N equals to 1, 2, and 3. Now if there's 3 there, okay, if N with 3 there, so if N is 3, so this water 3 and Cl 3 and 3. 3 minus 3 is 0, isn't it? So there are 4, right? 1, 2, 3, and there are 4 possible structural isomers. Now for this one here, right? For this one here, there's 1 chlorine here. So when you react with silver nitrate, right? 1 mole give you just 1 mole. So it's 1 mole here, there's 2 moles here, and there's 3 moles here for every mole of your structural isomers. Here there's none because all the chlorine, the 3 chlorine is attached datively to the chromium here, so it's very strong, they won't come out. So silver nitrate will not form any Pt3. The chlorine is held very strongly with the Cl3 plus, as they say here. Okay, chromium chloride here, right? It's not easily broken. So, so this bond here, right? So now with this in mind, I've got just, because here they say precipitate with silver nitrate, so I've got this to consider, and this to consider. Because this one here won't give you any PPT, so I don't care about this one here. Okay, right? Now let's look at the question. 1 gram, 1.00 grams of 3 of the isomers A, B, C, not 4, okay, were dissolved in separate samples of water. Right? So dissolve it, which means it dissolved means what? They will ionize to give you your complex ion, like this one here. Give you this part here. Okay. Right? And this part here. That means 1 mole will give you 3 moles of Cl minus. Okay, this one here, 1 mole will give you 2 moles of Cl minus and more water. So the Cl minus here will react with your silver nitrate. And this 1 mole here will dissolve, will give you only 1 mole of Cl minus, which will react with your silver. So here, if it dissolve, nothing will react because the 3Cl here is covalently bonded to chromium or datively bonded. So it won't come out. So there's no Cl minus here. So they say, well, dissolved, okay, an excess of silver nitrate was added to each of these 3. And the mass of silver, it means that only 3 of them, 1, 2, 3, 4, only the first 3 will be reacted, we mentioned, okay? So then the number of moles of silver chloride was then calculated. The table gives you for 1 mole of the isomer, sorry, 1 gram of isomer. So I found this number of moles of this is of course silver chloride. Okay, and so forth, so forth. Calculate the MR of this one. I mean, this is the molecular formula. This is a molecular formula. Molecular formula. The whole thing. So we found it to be 266.5. And we use 1 gram. So the number of moles will be 3.75 to the power minus 3. Which means in the first one here, right? Only 1 mole of 1 mole means 1 mole of this one here, right, gives you 1 mole of silver chloride because 1 is to 1. Yeah. Here, 1 mole of this one give you 2 moles. It means 1 is to 2 moles of silver. This is your Cl minus. This one here, 1 mole of this give you how much? 3 moles of silver chloride because this is 3. This is well 1.13 times 10 to the power minus 2 over 3.75 10 to the power minus 3 is equals to 3. Okay, 3 moles. Right? That means if 3 moles come out, then they say here, use the data in the table above to calculate the value of N for each of the isomers A, B, and C. Compare the table below and the values of N and the molecular formula for each of the isomers in the style of the general formula in the style of the general formula given below. Above. Okay. Show the working for this one. So you can see I wrote here. Right? So here 1 mole right? This is theory. One mole of this whole thing, this whole molecular formula. When dissolved in water, it gives you one mole of this complex ion and 3 moles of Cl minus. So if I start with 3.75 and take power minus 3 moles of this one, right now, if it's 3 moles, that means this one is what? N equals to 0. Right now, N equals 0, isn't it? Right? Because I have to calculate N, so N equals 0. See now, N equals 0 here. It means all the 3 Cl minus come out. N equals 0, Cl touch to it is 0. So here you can find, right? So 3 moles here. So 1 mole give you 3 moles. So 3.75 and 10 power minus 3 moles give you this one here, which is actually equal to how much? This one 1.3. This wrong here. 1.13 times 10 to the power minus 2. Right? It's one already, which means that the first one, of course, is when N is or C here is when N equals 0, isn't it? So C, N equals 0. Now, see, I wrote this down here. They want it in this form. You see? Because they say what? Now, if you put this on, I don't think they put it wrong, okay? They want in this form. Why? Because they tell you so. See? In the style and a molecular formula of each of the isomer in the style of general formula. So read the question carefully in general formula given above. See now, what's general formula? Now, it's a general formula. Okay, so put the 3 Cl3 down here, not 3 Cl minus, which means now this is the answer here. Okay, this one here. So this is the molecular formula. Okay, or the structural formula. Okay, which means this is 3 plus here. So here. Okay, now the second one. Okay, first 1, 2. It means that this is the 2 lah. Right? Sorry. Okay, N equals to 1. Okay, so when N equals to 1, of course, what? 2. When N equals to 1, here N equals to 1, 0. If it's 0, here is 3. When N equals to 1, the 2 is not. So 2 is the second one. 2. Okay? 2. So N equals 1. Right? Means 2 of the Cl minus comes out and you get 2 moles of the ratio is 2 moles of your silver chloride. So B is when N equals to 1. Okay? So now this is the formula. Right? And this is a normal way people write, but then they want it in the general formula like this. So that these 2 Cl minus here will write Cl2 down here and H2. Right? When N equals 2, you get 1 mole of silver. When N equals 2, right? N equals 2. So N equals 2. There are 2 Cl here and 1 Cl here. That's why you get only 1 mole of silver chloride here. So the formula will be this one here. Okay? One outside here. So this is the one that will be attacked by a silver nitrate. So this is the correct formula. Let's look at the marking scheme. Right? I think it's here. Okay, see now. Okay. Now see, they give here, right? Now the ratio 1/266.5. This is the number of moles. Okay, that's 1 mark. Okay, 2 marks for the whole thing. Okay? And this I don't know how to give it, but it's 2 marks only. Very simple. Okay, so the MR is 1 mark. Okay, now here, right? So you can see here, the last one is out. See the 3, right? They don't put like Cr H2O 6 bracket. This is actually 3 plus, okay? And dot 3 Cl minus. This is how we normally write, but they want it in the general form of this. Understand? So here is Cl2. Here's one here. So this and all this is 1 mark. 1 mark here, 1 mark here. Very simple, isn't it? All right. This is the one here. Now let me show you another question almost, okay? It's in page 137. This on top here. Go back and think over, okay? All right, here. See, if you ask me, how would you know I'm talking about structural isomers? Structural isomers normally appear for octahedral complex, or here for and the number of ligands there will exceed 6. Like this now. Like now here exceeds 6 there. See here? It's now here. Right? Here. This is the central ion. 6 plus 3. 9 1. See now? So there's a chance of who is going to be attached to the central ion. The central ion, if it's octahedral, can take only 6. Yeah, so 3 of them will be outside. It can be chlorine, it can be water, it can be a combination of both. So now that means you can see, I know now, as long as there are more than 6, 7 or 8 or 9, whatever is it, I can have structural isomerism, and you figure it out, okay? One by one. Now here is another one. You can figure out with me, okay? Here. All right. I figured out, so when you make time shorter for me to teach, okay? Bubbling air, very important. The bubbling air, that means oxygen is put inside, because they ask you for type of reaction, which is oxidation, through different aqueous mixtures of cobalt, chloride. Now this plus 2, okay? COCl2, isn't it? If you cannot see this, you cannot see maybe bigger, okay? See now, CO, it's not CU, COCl2. Ammonium chloride and ammonia produce various complexes ions with general formula. See now, okay? So again, you use the N idea, right? So remember, if you look at here, of course, N is a whole number. When N is 0, right, is cobalt, NH3 bracket 6. Cl don't have. The whole thing here is what? N is 0 is 3 plus. And the chlorine is what? N. Okay? There's no chlorine there. So, see, N is 0. Okay? N is 0 is 0. Okay? So this is the one. Okay? When N is 1, N equals to 1, the formula is, you can work it out. It's an exam, CO, NH3, 5, and Cl here. And of course, this is 3 plus. Okay? 3 plus minus 1 here is 2 plus. So step by step, you can work out here, right? So maximum, okay? See, the maximum of N will be 3, isn't it? No, can it be more than 3? Okay, because here can be more than 3. Okay, right? All right, so here you can see I put down here all the choices. All right, when N equals to 0, this is the one here, 1. When N equals to 1, Cl is 1 here, so NH3 is 5. Okay, 2 Cl minus on the outside. Okay, because why 2 Cl? Because you need to balance off. So if it's plus 3 here, you need 3 Cl minus here. Or like the old question here, right in the general formula for molecular formula will be CnH3, 6 bracket, Cl3 at the bottom here. Okay, so instead of putting 3 minus here, I put a 3 minus here because it's easy to see that, well, it's iron as well. But this is a general formula, the way they put it in the earlier question. This one, of course, this one is when N is equal to 1. So 6 minus 1 is 5, so current is 1. So 6 again, this both are what? Octahedral, isn't it? Octahedral complex. So what is negative 1, this minus, this plus 3, so it's 2 plus here. So of course you get 2 Cl minus here. Now of course the general formula should be CO NH3 bracket 5 Cl bracket N Cl2 at the bottom here. Right? And of course you want to put completely put NH3 here. Okay, so this whole thing will be the general molecular formula. And when N equals to 2, right? 6 minus 2 is 4. So 2 here, right? So 1 Cl here. See now, and 2 here. When N equal 3, 3 here, with 3 here, 3 cell, and here. See now. So there are 1, 2, 3, and 4 structural isomers. Okay, so you have a view of how you can slowly, one by one, replace the ligands. And on the octahedral complex, the one which is replaced will come up as ion here, or as a free molecule, okay, which must be included in the molecular formula. Okay, now determine the oxygen states in the complex of this. Of course, all of them are +3. Remember, put +3, don't put 3 plus, okay? +3, right? All right, next one here. Name the 2 types of reaction undergone by complex ions during the formation of this complex. Of course, +2 to +3 is +2. Going to +3, of course, here. The first one is oxidation, isn't it? Oxidation. Why? Going from +2 cobalt to +3, or rather +2 plus here to cobalt 3 plus here. We don't want this one. Okay, to be sure, right? Yeah. Okay. The second one, of course, is, remember, one by one, the ammonia here is being replaced, okay, or substituted or displaced by chlorine, Cl minus. Okay, from here to here, right? From here to here is called ligand displacement, okay, or they call it a ligand, well, exchange. So normally they use ligand exchange, okay. 2, the reaction is called it's called ligand exchange, or ligand exchange, or displacement, or replacement. Now let's look at the marking scheme. The marking scheme here. That day, I'm sorry, I just didn't figure it out. So today I figured everything out. Okay, is it here? Don't tell me I didn't get it again. Simon, yeah, never mind. Okay, maybe it's here. Yeah. Here, correct. See? Okay. Oxidation. See now. Right. Oxidation. Right? Because CO2 plus going to CO3 plus. Right? Oxidation. The first one, okay, I told you, they ask you for what? See here? They ask you for the oxygen state. Always positive first, no. Okay? Whenever they ask for oxygen state, always positive followed by the number. Right? But in the formula, the number is first, followed by the sign. This is the conventional way. Okay? So 2 types of reaction here, oxidation and ligand exchange, or here, what? Here's oxidation, or say ligand displacement can, ligand replacement can, ligand exchange can, or ligand substitution. There are 4 choices for input. Normally, you can see that ligand exchange is most popularly used in the marking scheme. Okay, replacement can, okay, it means you one ligand kicked up by another ligand because form stronger bonds. Okay, let's see. Okay, now here we have the complex, right? Remember, see the whole thing complex, 4 plus 2, which means what? Coordination number 6, which means what kind of complex? Octahedral, shows isomerism. Draw 3-dimensional structures of the 2 isomers, suggest the type of isomers. Of course, this one, of course, is a cis-trans. Remember, I thought is M. Still, this is a complex number. This is cobalt. Okay, plus 3 plus. Okay, right. Ma4B2, whatever. Okay, the whole thing is charged. The charge is important here. A is your ammonia. B, what? Of course, in this case here, you get cis-trans, right? So you draw. Now, the drawing, you must always remember, even if they don't ask you, even the sign marking don't have, draw in 3 dimension, cobalt here. Okay, coming out here, like that. No, you use the normal way of drawing your 3-dimension as shaded. Okay, like in your AS for your what? For your well, optical isomerism. Okay, and then go back. Okay, can big to small, small to big. Okay, so this ammonia and H3 and H3. Right now, depends on here. Here put NH3 as well. You want to draw the trans, which is top here, straight line, straight line. Here Cl and Cl, yeah. Okay, and it's 3. Okay, this whole thing is 3. Remember, this 3 plus now. Okay, this whole thing is 1 plus. Like that. Okay, this is your trans isomers. Of course, the second one, of course, again, you draw the 3-dimension. It's called a 3-dimension drawing. Okay, make sure don't waste your time getting 0. Okay, like that. And here's can big to small, small to big. I'm like small to big. Okay, I put that one first. Chlorine here, and chlorine anyway with that. Okay, here goes again, here again. Okay, okay, there's ammonia here. H3 and H3 and H3 and one more here, straight line and H3. Okay, so you can see, draw 2 isomers, suggest the type of isomers. Okay, what is this? Cis-trans, right? Cis-trans or geometrical. Okay, right. Now let's look at the marking scheme. Okay, see now, see, they draw the 3-dimensional. See the hard line. Okay, right up here. Right. Now this is called this cis. Right, can be here or the side here again. Side here again. Same as it. Right, you take a model up and down the same. Okay, trans opposite each other, or can be opposite each other on the square planar here. Okay, cis-trans isomerism. Okay, right. 1 plus 1. 2 of them. They didn't say name or what here, but better put a name. Okay, here they give name, cis-trans isomerism. Okay, right. So you can see how they're being asked. So these 2 questions I show you, they are octahedral complex with structural isomerism as well as cis-trans isomerism. Right. Now let's go to coordination number 4, square planar. Okay, I'm going to use let's go back to the question first. It's 25. Oops, smaller again. Okay. Remember here, I told you here, see, tetrahedral and square planar both have the same coordination number. They will tell you. Remember. The 4C C. Okay. Copper chloride, copper 2 chloride. Remember, if it's a transition metal, that means 4. If it's just CuCl2, that means it's not transition metal. It's just copper chloride salt. CuCl4 2 minus is a complex ion because the number of ligands or the number of donor atoms or the number of daily bonds formed with the copper 2 plus exceeds the normal covalency. That's why it's called complex ion. Okay, right? And that's why the complex ion is no longer like here. It's not covalent bond. This is ionic bond. It's 2 plus and this 1 minus. This is ionic bond, but this is a covalent bond. So you can see the difference now. Covalent bond exists in complex ion. In this case here is ionic bonds. So there's a difference. So for covalent bonds here, they will form shapes. Remember, AS, it forms here either a tetrahedral or square planar. Now, if it's copper 2 plus, cobalt 2 plus, chromium 3 plus, chloride, they will always form tetrahedral. Some books say because the Cl minus is big and they repel each other, they cannot form a square planar. And you must remember nickel and platinum always form a square planar. It's easy to remember, isn't it? NP, right? No problem, 1, okay? Or copper, C. Find some way to remember this, okay? Octahedral is quite simple, 6, okay? Right now, let's see. How do we deal with this? Okay? Now, I'm going to talk about optical isomers after, okay? Okay, we're still with cis and trans. Cis and trans we talked about for octahedral complex, and now cis and trans for your square planar. Okay, now here I give you the square planar, cis and trans. Okay, that means the square planar is MAB2. Of course, M is a central ion, like for example, platinum. Okay, PCl4 minus this, right? This is your Ma4, that's all. Okay, but cis and trans, even you have got Pt, NH3, and Cl3. This also, this one is not 1 here, 4. This is also a square planar, but this one here, so this is Ma3b. You know? So here there's no cis and trans. For square planar, cis and trans happen with Ma2b2. Of course. Now let's say I draw it out for you. Here, right? Let's say for example, Pt NH3 bracket 2 Cl2. Okay, the whole thing here charge. Platinum is +2. +2, this is charge 0. Okay, right? So in this case here, this one here, platinum square planar. Okay, so I draw square planar. Platinum here. Now, ammonia can be on here and opposite each other. Here you will Cl and Cl. Okay, so this is opposite, it's called trans. Okay, now the other isomer, of course, will be the cis. You can put anywhere like ammonia here and ammonia here. Okay, and Cl here and Cl here. This is your cis. So there are two. This is your cis-trans isomer. Okay, right? Same name, just got cis-trans, and that's all. Now let me show you some of the examples here for square planar. Okay, so you would be more adequately in answering the questions. 130, 130. Okay, let's go in order. Okay, 130 here. It's got lots of variation. Like here. Okay, the perfect example. There are two isomeric complexes with the formula of Pt NH3 2Cl2. Because now this is platinum is +2, isn't it? 2 plus 1, chlorine is 1 minus 8. So overall is +2 and -2 because of 0, isn't it? That's why. Okay. One of them is an anti-cancer drug. Okay, I'll show you why. Okay. This is quite common. They ask you why is anti-cancer drug. Okay. Draw diagrams of showing the three-dimensional of the two isomers. It's simple, isn't it? Right? I told you before just now. So you must draw. Okay. Nice square like that. Okay. Platinum here, and of course, like that again, coming out here. Okay, coming out here. Learn to draw them, don't be lazy, okay? Okay, and pop. No, sorry, no time bottom. I thought about octahedral, my friend. So, decide. Okay, if it's ammonia here, must be Cl here and Cl here. I know, if the same side, it's your cis. I know. Okay, draw another one. Okay, platinum. Coming out here. Okay, don't have to be an artist. Just draw simple ones. Cl here and Cl opposite each other. Ammonia here, opposite each other. What we got? Of course, your trans isomers. Yeah. Okay, and comment the polarity of the two isomers. Now, of course, this one go to here, this one go to here. It means this is more polar. This is delta, negative, delta, negative. So this one go to here. That means that they will cancel each other. Right? So of course, who is more polar? This is more polar. The cis is more polar. Cis, right? More polar. Why? Because the charges do not. Okay, up here, do not cancel each other. Do not cancel off each other. But the trans does. Okay, now let's look at the marking scheme first. I think I got it step by step because I don't want to be idiot again. Okay, here. I think so. I hope so. Yeah, correct. Yeah. Okay. So remember, right? Coming out like that. Okay, the blue lah. See? Shade. Okay. Draw this one better. Just to so the cis on the same side. Cis. Okay, trans. So cis is more polar. Okay, right? Okay, right? Okay, okay. Why cis is more polar? As the dipoles do not cancel each other. Okay, it's one mark only. Okay, cis is more polar enough. Okay, do not cancel each other. Okay, trans is non-polar because the dipoles cancel each other. Okay, so what I missed down here is the dipoles. Okay, charge because the charge of the dipoles do not cancel each other. Now here, you see, how does this act as an anti-cancer drug? So here, it's a cisplatin. Okay, see it's on here. See the cisplatin. Let me just show you how now. Now this is a DNA, two strands up. The two strands here. It's a hydrogen bonds, right? In cancer, what happens is they will split here, and they will multiply. They will split here and they will multiply. Okay, that's why cancer got growth. Is it? That means the cells grow very fast and they non-stop growing. So you get a tumor. So cell replication is by DNA splitting. Isn't it? So now this is the DNA. So what it does is the cisplatin. There are two ways you can do it. Platinum here, and the Cl here, and the Cl here. Right? See, cis there. It's ammonia here. They form once they split out here. This fella here will reproduce it. So the genetic factor here or the amino acids here will form another one. So you bond to here. See, bond to here. I mean, bond to here, that means that this part cannot replicate the cells in, so it stops replication. So it stops the growth. See now. So this cisplatin, only the cisplatin can do it. So it's called cisplatin. Okay, because the chlorine here, they bond to this chain of the DNA. Okay, and prevent this part here from completing the protein to form the cell. So it stops the growth. Okay now, right? Okay, now here, another question here. Oxaloplatin is not a successful anti-cancer drug in which the stereochemistry of platinum is same as this one here. Okay, so it is like cis. Okay, trying to here and here. Okay, right? Explain why there are no isomers in this one here. Okay, no isomers. Right now, let's see how the answer is. No isomers. Okay, see the one here. Okay. Top here, sorry. Not this one. Okay. Okay. Now, see this can only be cis. Okay. Right. Because here this can only be cis. Its mirror images is the same. Now this one you talk about it later when you talk about optical isomerism. Okay. Now here there is another reason. The distance between the two co-nitrogens oxygen is too small to bond with the trans. That means, see, now if trans, okay, so here and here, right? These are cis. To trans, move up from here to here, no, right? A longer bond. See, a longer bond. It's difficult for the NH2 and O to exchange places. Okay, it's the two covalent ends are too small. It means this is too small to form a trans bond. See, okay. So like here, you see. Let's go back here. Right. It means that this bond here, right, is too short. Right, too short to form. This is cis there. To form a trans bond. Okay. The best, of course, is later you see that when we draw optical isomers, right? Why there are no isomers? Actually, it means you can say, well, there are no optical isomers. Okay, right? That's why there's no isomers. That's what the answer here gave. So the idea of seeing how the answer is, the image is the same. Okay, right? Because you put the mirror of the shoulder. Okay, the mirror images here, they're the same as this one here. Okay, so we won't go to that now. Okay, right. All right. Now here another one here. Okay, now here's only one structure of the complex nickel. R3P, don't care. Now this whole thing is 1. This whole thing is 1. So 2. Chlorine is 2. Okay, so it says here R is CH3, is R. Okay, R, let me CH3 bracket 3 and P. P, okay, this is a monodentate. That means that it can form one dative bond with the central ion atom nickel. Okay, right? So means 2 plus 2, 4. Okay, 4. That means if four coordination number. Okay, it must be either tetrahedral or what? Or square planar. Okay, so now you can say, well, what does this indicate about the stereochemistry around the nickel? Okay, see, if only one structure, okay, because see, if it's square planar, it is Ma2B2. If it's square planar, it can be cis and trans, cis and trans. Because, see, if it's square planar, if I put nickel here, and I put the R3P here and R3P here on here, and here is a Cl here, is a cis. If I put Cl here and Cl here, and R3P here and R3P here, this will be what? This is a trans. It means there are two structures, there are 2 isomers. So there's only one. It means it must be a tetrahedral nickel. See now? Okay? Okay, it means C. And for tetrahedral to have isomers, it must be optical isomers. It means it must be 4 groups here. Okay? So, but there's only 3, there are 2 different groups here, R2P. So sometimes nickel can show you that is a tetrahedral sometimes, but normally it's a square planar. Okay? R2P, R3P, Cl here. No. So this, okay, if you do a mirror image, they will superimpose, because unless the 4 groups here are different, it can give you your optical isomers. So draw a 3-dimensional to show easy. Nickel here, okay? Remember, draw the straight line first. And then the one coming out here. And then the one going behind, okay? You can put R3P here, R3P here, and of course Cl here, okay? Right, okay, let's look at marking schema. See, okay, see? It's not a square planar, but tetrahedral. See, must be 3D, see, must be 3D tetrahedral like, okay? See now, one coming out, okay? Right? And of course, either this or this, because it doesn't matter. Okay, can exchange this, whatever. Right? So you can see here how they come out. What this indicates, so it means this about the stereochemistry around. What does it indicate about the stereochemistry around this nickel? All right? It means it must be tetrahedral. The stereochemistry. Tetrahedral. Not square planar. Okay? See the marking schema? Not square planar or tetrahedral. Okay? So you can see this how it comes out in all this. Now I've got 5 more minutes. I just want to go on a few more examples to show you, okay? 315, 135, sorry, 135. All these are examples, but they are the same. Once you get the hang of it, it's quite simple. Now here again, you see, always square planar or tetrahedral, they will tell you 2 isomers or 1 isomer. Okay. Now there are 2 isomers with the formula nickel, same one, nickel R3PI2, right? See, 2 plus, a bit bigger, see, 2 plus 2, probably first. What is this? Okay. Okay. Right now, here 2. See, they tell you R is alkyl, R3P is a more than that. So 2 here. 2 plus 2 is 4, isn't it? Right? 2 plus 2 is 4. So either is a square planar or is a tetrahedral. But only one structure, that means see now. Okay? With the formula of, see, here there are 2 isomers with this formula. Remember, it's M(A2)(B2). That means it's a cis-trans. No? But only one structure for this one here. Now this is also 4, no? 2 plus 2. That means if there's only one structure, that means this must be tetrahedral. See now? Right? Simple enough. So whenever there's coordination number 4, it's either a square planar or tetrahedral. For square planar, if it's M(A2)(B2) formula, general formula, it will be cis and trans. Right? For the other one, of course, if there's only one structural isomer, it can be tetrahedral. But of course, if I got cobalt, okay, IBrClF. This one here, if it's tetrahedral, it will have what? You have positive and negative isomers. Yeah, if it's tetrahedral, it means it have a mirror image. Cobalt, remember? IBrClF. You can work out yourself. Okay, here, time is catching up with us. Okay, so now draw the 2 diagrams here. I'm going to put it smaller. Okay, right? That means here, this one here got 2. Right here, square planar. Very simple. Remember, it must 3D. Okay, square planar. Right? This is your nickel. Nickel is normally square planar. Okay, coming out like that. Remember, always practice. Perfect practice makes perfect. Perfectly practice it. Okay. All right. Remember, put I here and I here. Okay. First is 2 plus. 2 plus here. Right. This minus. Yeah. This is your R3P. And of course, this is your cis. And this is your trans here. Okay. Nickel 2 plus yeah. Okay, this is your coming out here. Okay, if it's I here, means I here. It's your trans. Of course, it's your R3P here. Okay, and of course, in this case, this for cobalt, right? It's a tetrahedral. So cobalt here, they put it so nicely for you here. Okay, cobalt, CO. Okay, draw a straight line first, and this is coming out. It's going back. Okay, up to you. I doesn't matter. I is your PR3. Okay, so it's 3 marks here. Let's do I have a marking scheme here? I think I have. Yes or no? I don't have. So, I thought I have. No? I thought I did it. Never mind. Okay, I'm correct anyway. Okay, I don't have it here. Never mind. All right. So this is quite simple. Now time is up. I would go into more types of examples for tetrahedral, octahedral complexes, which have biligands, which have got also different kinds of optical isomers as well. Okay, so I'll probably do one tomorrow. Okay, so goodbye and Happy New Year again. So I'm trying to stop the whole thing. Okay, stop recording. Bye-bye.